In summary, you must know the advantage of the Gaussian elimination over the conventional methods, such as the inverse method, graphical method, Cramer rules, and the method of elimination. So Gaussian elimination has huge advantage in terms of computational efficiency. For a large number of equations n greater than 3, we will use this type of computer method instead of the conventional method. So the conventional method normally is only stable for number of equations less or equal to 3. You must know how to apply the Gaussian elimination to solve the multiple linear equation. For example, we have a matrix formulation x equal to b and we are going to find the unknown x. So in this case, we need to perform the forward elimination in order to obtain the A matrix in this upper triangular format, where you need to have 3 0 at the non-diagonal part here. For a 3 times 3 matrix, then you need to perform the back substitution, or what we call the backward substitution, to find the unknown x3 first, followed by unknown x2 and x1. So these are the two main steps in the Gaussian elimination that you must know. You also need to know and understand the function of determinant analysis. So why we perform the determinant for the matrix A, where your A is equal to the system matrix. You must also know why you need to perform determinant together with the scaling. Without the scaling, the determinant result is not reliable. So with the scaling, then only the determinant result is reliable. Scaling has two functions. One is to standardize the size of the determinant so that you can correctly perform the determinant analysis to tell the actual system condition. The second function for the scaling analysis is to check whether you need to perform the pivoting strategy or not. If the pivot element is maximum, then you do not need to perform the pivoting strategy. So if you have small pivot element, then you need to perform the pivot strategy. In this case, you need to switch the row 3 to the row 1 so that you obtain the pivot element to be the maximum value. And this is called the partial pivoting. So after the partial pivoting, you should be able to obtain the pivot element to be the maximum value compared to other rows. Partial pivoting is very useful to reduce the problem due to the divide by zero issue. In general, this is the recommended Gaussian elimination with partial pivoting procedure that involve the various analyses, such as the determinant, scaling, and pivoting. Given the problem Ax equal to b, in the step 1, we need to perform the scaling analysis in order to standardize the determinant for matrix A, and matrix A is your system matrix. After you scale the matrix A, from the scale coefficient here, we can tell whether we need the pivoting or not. Assume that this is the result of the matrix A after you perform the scaling. Then you see the pivot element here is not the maximum compared to other rows. So you found the maximum element at third row, so you need to perform the pivoting to switch the row 3 to row 1. So we need the pivoting strategy if the pivot element is not maximum. After you perform the partial pivoting, now you check the pivot element which is the maximum now compared to other rows. So we can conclude that the partial pivoting must be conducted where the row 3 must be switched with the row 1. In the next step, we can use the determinant on the matrix A that has been scaled to check the condition of the system either is singular, if condition, or well posed. You need to be careful. Don't perform the determinant on the matrix A that has not been scaled. So if you perform the determinant on the A matrix directly, this is not valid to check the condition of the system. So you have to use the matrix A that has been scaled. Only this is valid to check the condition. If you get the answer to be 0, then we can say it's a singular system. If you get it approximate to 0, let's say plus minus within 0.1, then we say it's a ill condition. If let's say you have answer not equal to 0 or far away from 0, then we can say it's a well-conditioned system. In the next step, you need to perform the pivoting on the original coefficient instead of the scale coefficient in order to reduce the round-off error. So we go back to the original equation here and then take the partial pivoting row 3, change and switch to the row 1 in this original coefficient. And then proceed from here. You can perform the Gaussian elimination, which is the forward elimination and also the backward substitution to find the answer. And once you get the answer, you should verify your answer by checking the left hand side and right hand side. If they are equal, then you get the correct and accurate answer. This is the example of solving multiple equations by using the recommended strategy. So instead of writing it in the conventional matrix format, so since x1, x2, x3 are remain in all the calculations, therefore we can use the augmented matrix format to save the time in writing the x1, x2, x3. In step 1, we perform the scaling analysis to standardize the matrix, as well as check the need of pivoting. To perform the scaling, we only check on the right hand side, which is the system matrix. So we check row by row. So in the first row, you have the 7 to be the maximum element. So we need to divide 7 to get the scaling result. So you can see in the first equation here, we divide it by 7. In the second row, we have 3 to be the maximum element. Therefore, we divide 3 in the second equation. Next, we have 10 in the third row to be the maximum element. So we need to divide 10 in the third equation. So this is your scaling result. Where you see we have maximum element to be 1 in the system matrix here. So we can say that the standardization of the matrix is successful. To check the requirement of pivoting, we need to refer to the pivot element here and compare to other row. So we found that in the second row here, your element is the largest compared to the first row. Therefore, we need to switch row 2 to row 1. This means that we need the partial pivoting here. In the second step, we perform the pivoting strategy to reduce the effect of divide by 0. So in this case, we switch the 2 to 1, 1 to 2. Then you obtain this result. So now you can see that the maximum element is 1 compared to other row. So the partial pivoting is successful. Then we continue to perform the determinant analysis on the matrix A, which has been scaled. So you obtain the result to be 1.002. So this tells the system condition where you obtain the determinant not equal to 0, which means it's a well-conditioned system, and we can obtain unique solutions here. In the next step, we perform the partial pivoting using the original coefficient here instead of using the scale coefficient here. So we do not proceed the Gaussian elimination with partial pivoting from here. No. So from here, since we know that we need to perform the partial pivoting by switch the row 1 to row 2. So therefore you can see the first row here is switched to the second row. And you have the second row here switched to the first row. And don't forget, for the augmented matrix format, you need to have a line here to indicate the system matrix and the right hand side function. Then we can continue to perform the Gaussian elimination by taking the forward elimination for these two components to be 0. This can be done by using this factor and the equation here. During the calculation, try to retain or keep the height significant figure. For example, in this case, you have 1, 2, 3, 4, 5, 6, 7 significant figures in order to reduce the calculation error due to round-off error. And then you can continue perform the forward elimination by let this equal to 0 using this equation. And then you continue with the back substitution to find the x3 first. From this equation, followed by solution x2 that can be found from this second equation, and then lastly x1 from the first equation. So this is the backward substitution. So once you get the answer, to check whether you get accurate answer or not, by substitute the solution x1, x2, x3 into the left hand side equation, and you compute it to be this answer. When you compare it with the right hand side solution, you found that left hand side is equal to right hand side. Therefore, we can conclude that this solution is accurate.